Good afternoon, Year 10. This video we're going to have a look at the questions that we did last week on stopping distance. I'm going to model the correct answers. When we get to the 6-mark question, if you haven't got at least 4 marks, I'd like you to look at how I lay out my answer, and then I'd like you to redraft yours. Question 1. A car is moving along a road. The driver sees an obstacle in the road at time equals 0 and applies the brakes until the car stops. The graph shows how the velocity of the car changes with time. Remember, when you have these questions, you'll either have a velocity time graph or a distance time graph, or displacement time graph sometimes. And which graph you have determines what you're going to do with it. Which feature of the graph represents the negative acceleration of the car? So what we need to remember is that acceleration is represented by the gradient of the line on a velocity time graph. Acceleration isn't represented directly on a distance time graph at all. So which feature represents the negative acceleration? Well, it's this negative gradient of the car when it starts braking. So the gradient of the sloping line. Second part, which feature of the graph represents the distance travelled by the car? The distance travelled on a velocity time graph is the area underneath the line. So it's this total area in here, bounded by the axes and the line. If we were asked to calculate it, if there were numbers on here, then we'd have to break this down. There's a square here, so we do base times height, and there's a triangle in here, so we do half base times height. It's not asking us for that though, it's just asking us to tick the area under the graph. On a different journey, the car is moving at a greater steady speed. The driver sees an obstacle in the road at time equals 0, same as before, and then applies the brakes until the car stops. The driver's reaction time and braking distance are the same as shown in the graph above. On the graph above, draw another graph to show the motion of the car. This is a very tricky question, actually. Specifically because the braking distance is the same. But we'll have a go at it and see how we do. First of all, we need to add a line. So the car's moving at a higher initial velocity. So that means this line is going to be higher up, at a higher number on the velocity y-axis. So we need to draw a line going across. But we need to make sure it's the same length as the line down here. Why is it the same length? Well, because the reaction time of the driver is the same. His thinking time is the same. And you can see that his thinking distance is therefore larger, because the area underneath this line is larger than it is under this line here. Now this is the really tricky part. It says that his braking distance is the same. We'll scroll down and make sure that's the same. So not braking time, but braking distance is the same. So that means that actually, even though he's going faster, his braking time is going to have to be smaller, because his braking distance, the area underneath the graph, is the same. So the area under this triangle here is going to be the same as the area under the triangle that we're going to draw here that brings us down to a stop. Now, it really depends on exactly what your velocity is, and there will be some fairly generous leeway in making sure that you have the right answer. So if it's off by a tiny amount, it won't matter too much. But it means that our velocity is going to reduce more quickly. Our deceleration is going to be faster. So I'm going to suggest it's something like this. And now we can see and imagine that the area underneath this line here while he's braking, so that's the triangle, the area of this triangle here is similar to the area of this triangle here. When I look at it, well, that's perhaps not exact. And I think that I might have made a small mistake here because it seems like my reaction time is actually a bit shorter than it should have been. But broadly speaking, that's correct. Lots of people would answer this by saying that the gradient's going to be the same, his deceleration is going to be the same, which would often be the case. But you can apply brakes more strongly to on a car if you need to. Okay, this is the 6-mark question. You will be assessed using good English, organising information clearly and using specialist terms when appropriate. Now, I want you to note that you're going to get marked on organising information clearly, so it should be nice and easy for the examiner to read. Thinking distance and braking distance affect stopping distance. Explain how the factors that affect thinking distance and braking distance affect stopping distance. So this word explain is vitally important. It's not enough just to state the factors. That would be valid for a 3-mark question. Maybe state some factors that affect braking distance and and thinking distance even. Describe might be a similar sort of idea, but explain, we're going to have to say why they affect stopping distance. So, I'm not going to write this out in full. I'm going to show you my thinking as I go through this. So first of all, I will start out with a statement that's similar to what's already been given to me. It might not be scoring, but the idea that stopping distance is equal to the sum of braking distance and thinking distance. We know that. It's already kind of been given to us, but it's a more obvious, explicit way of laying it out. I have to explain how factors that affect these two things affect stopping distance. So I can immediately break this down into 2 separate sections. Braking distance and thinking distance. Now I have to wrap my brain. Do I remember all of these factors that affect braking distance? Well, anything to do with brakes. So yep, brakes, brake condition, road conditions, speed, those are the only ones coming to my mind right now, so we'll leave it there. What about thinking distance? Well, we have, for example, drugs and alcohol. We also have distractions. We also have speed. Removed one more from braking, and that was the mass of the vehicle. Is this all of them? Well, no, I know I'm missing some, but I do have a good variety of different options here to talk about, and they affect the braking and thinking distances in different ways. So, when I look at braking distance, why does the condition of my brakes and the condition of the road affect braking distance? Well, they determine the amount of force that can be exerted by the brakes. So, the brakes, the condition of the brakes, limits maximum force, and that's true for road conditions as well. So, have we fully explained this? Well, arguably, we could probably say changes acceleration as well. Remembering that F equals ma. How does mass affect braking distance? Well, it changes acceleration. And perhaps here we can mention F equals ma more distinctly. How does speed affect your braking distance? Well, higher speed means more acceleration or more deceleration required. Going to thinking distance, drugs, alcohol, and distractions all work in the same way. Increase reaction time. Increase reaction time. Increase reaction time. All of the thinking distance ones like that work in the same basic way. How does speed affect thinking distance? Well, the faster you're going, the further you go for the same reaction time. So higher speed increases distance for the same reaction time. Here we've mentioned 8 different factors, or 7 factors because speed appears twice, and we have 5 different explanations. So as long as we lay it out like this, use full sentences. What I have here is the structure, the thing that I'm thinking about. It's not necessarily a full answer. It's not necessarily going to score 5 or 6 marks because I haven't formed it into sentences. So you might get away with doing lists like this, but always try to follow the instructions and put it into full sentences. Okay, quickly talking through the Do Now Forces knowledge check from last week. How do you calculate weight? Weight is mass times gravitational field strength. 2. If my weight is 1,000 newtons, what is my mass? This is a rearrangement of the equation we just said. So weight divided by gravitational field strength is mass. So 100 kilograms. 3. A scalar has magnitude, or size, or an amount. A vector has that, but it also has direction. 4. Newton's second law is F equals ma. Force is mass times acceleration. 5. If a car moves at 10 meters per second, but no forces act, I guess it's in space, what happens to its speed? Nothing. No force, no acceleration. What is Hooke's law? Hooke's law is from forces and elasticity. Force is proportional to extension. So it's a straight line through the origin. If you increase the force on the spring, then you increase its extension proportionally. How many forces are needed to elastically deform an object? 2 or more. If I'm moving at 2 meters per second, I walk for 30 seconds, how far have I gone? Distance is speed times time, so 2 times 30, 60 meters. I start at rest and reach 5 meters per second in a time of 10 seconds. What's my acceleration? So I start at 0, I go to 5, so the change in speed is 5 meters per second. Acceleration is change in speed divided by time. 5 divided by 10. 0.5. 10. What does the gradient of a distance time graph represent? So, unlike the question we did in the past paper questions, the gradient of a distance time graph is the velocity of the object. Okay, this was an interesting question. It's interesting partly because it says, write a short conclusion explaining what these graphs show for 4 marks. Because there's 2 different things on this single graph. It's kind of like a nested bar chart. It's a very strange kind of graph that we don't see very much. But let's have a look at, first of all, thinking distance and then braking distance and see what we can say. Thinking distance. If we look at the distance travelled while thinking at 20 metres, it's about a half of what it is at 40 metres, or about a third of what it is at 60 metres. So the first thing we can say is that thinking distance is proportional to the speed of the car. So when the speed doubles, the thinking distance doubles. We can also look at 30 and 60, and again we'll see that it's about doubled. What about braking distance? Well, if we look at 20 and 40, we can see that when we double the speed, the braking distance goes up by a lot more than double. Just looking at the blue part, not the red part now. Just the blue part. When we go from 30 to 60, yeah, it definitely a lot more than doubles. It looks like it kind of quadruples nearly. So we can say that as speed increases, braking distance increases faster than thinking distance. It increases at a greater rate. And then, finally, we need to say what's actually showing. Well, we should remember that braking distance and thinking distance together form stopping distance. So overall, this shows that stopping distance increases as speed increases. And because of the contribution of braking distance, it doesn't increase directionally proportionally. It increases faster than directionally proportionally. If we double our speed, we more than double our stopping distance. These last few questions should have been reasonably straightforward. How would being tired affect a driver's reaction time? His reaction time would be slower. How would a wet track affect the braking distance of a go-kart? We don't have to explain it, but a wet track would reduce friction, so therefore it would increase the braking distance of the go-kart. How do the two graphs show that the cars have the same deceleration? Remember that deceleration is shown by the gradient of a velocity time graph. Both have the same gradient on their deceleration sections once they have actually started braking. We can see that because it goes between 0.6 and 3.2 seconds. So that is 2.6 seconds. And then it goes between 1.4 and 4 seconds. So again, 2.6 seconds. It takes the same time for them to stop from the same initial velocity. How can you tell which driver has been drinking alcohol? Well, car B has a larger thinking distance because driver B has a longer reaction time, a slower reaction time. So B must have been drinking alcohol. Okay, let's go through these science skills questions. What conclusion can be made from this graph? This is very similar to the graph we just looked at. Shortly, we can just say that as the speed in meters per second of an object, like a car, increases, braking distance increases. That's not probably quite enough yet, though. We can say that it increases faster as speed increases. It's quite a clunky way of saying it, but we can say that at low speeds, braking distance is only increasing slowly, but at higher speeds, it increases faster. Draw a line showing what's like it happened to the braking distance at different speeds if the same car was driven on an icy road. So how would this be different on an icy road? Well, we know it's have to start at zero. If you're not moving on an icy road, you don't need to brake. But we do need to think, how quickly would it increase? So an icy road will always have less friction than a normal road, so that means that your braking distance is going to be higher at all speeds. So this will be a steeper graph. So I'm not going to try and draw the line, but if you follow where the cursor's going, it will be a steeper line at all speeds. It will never be less steep. So always be above and always be steeper. The local council must decide whether to introduce the lower speed limit on a lot more roads. What evidence should the local council collect to help make this decision? This is an interesting question because it comes down to whether or not the information given to us is useful or not. You have to think, why do we want to reduce the speed limit? Well, because we want to reduce accidents. We want to reduce the severity of accidents. So, what evidence should they collect? They should probably try a trial. They should reduce the speed limit on an individual road. And they should see whether there are fewer accidents and also whether those accidents are less severe if fewer people end up going to hospital or dying as a result. Remember, you have to have an independent variable and a dependent variable. What are you going to change? The speed limit. What are you going to measure? How many accidents there are? And potentially as well, how severe the accidents are. State 3 factors that could affect the thinking distance of a stopping car: drugs, alcohol, distractions, fatigue or tiredness, and speed. Any of those. No explanation required, just state.